Good morning, early afternoon. I'd like to welcome you to our Visionaries series about the power of innovation, which you will surely see demonstrated today. I'm Ellen Partridge, the Deputy Assistant Secretary for Research and Technology here. New technologies are inherently disruptive because transportation touches everything that we do. When there is a disruptive technology that is touching transportation, we begin to pay attention. So for the average person, printing is a process involving paper and ink. The idea that in a matter of minutes we can actually, do wind turbines or, massive kinds of things is the stuff of science fiction, and yet it is actually real. So today we are going to hear from Dr. Lonnie Love, who is the Distinguished Research Scientist and Group Leader of Oak Ridge National Laboratory's Manufacturing Systems Research Group. So he is the project lead of what they call the Big Area Additive Manufacturing Program, also known as BAM. The program is advancing large-scale, high-speed composite and metal additive manufacturing, including commercial motor vehicles. Lonnie Love is a true innovator and thought leader working with industry partners to transform the potential of a game-changing innovation into commercially viable technology that will have far-reaching implications for transportation. He is also a passionate advocate for STEM-related education and is working with the first robotics program with school children. We're thrilled that Dr. Love has taken the time to come here and talk with us. I first heard about this program on NPR, and he was gracious enough to just respond immediately. So thank you very much. Join me in welcoming Dr. Love.
Thank you. This is exciting. I think we're at a. First off, I appreciate you guys inviting me here. We're at a what I think is a critical time in our country's history. Manufacturing is, to me, the foundation of everything we do. Taking raw material, and making good products. And we're seeing a resurgence in manufacturing in the United States. I was talking to Pat during lunch, and there's been after World War II, the U.S. led the world in manufacturing. Something interesting happened. Everybody's manufacturing infrastructure got decimated except for us. I remember as a kid watching Hogan's Heroes, and it was like every episode they're bombing a ball bearing plant, So in war, you're trying to stop the other countries from their manufacturing processes, and we were immune to that. And so after World War II, we had this huge insurgence. We were making for the world. Remember Made in America? Now we see Made in China. and so I think we're on the cusp of getting back to where it's Made in America. And it's very exciting. And a lot of it is not the manufacturing of our fathers and grandfathers, where manufacturing's going, which has me excited. And like I said, working with high school students is a real charge. It's not manufacturing your parents, it's manufacturing your kids. It's very tech savvy, and this generation of kids coming up is perfectly poised for this new area that's blossoming. So let's see if I can figure out how to change the channel here. That way. So I can't advance. Yeah, I'll just tell you, if you can just go to the next slide. So how many of you heard of additive manufacturing? It's actually a relatively new term. It started out as 3D printing, and 3D printing actually has been around for 25 years. Most manufacturing, you're taking you're taking raw material and whittling away material to get to your final part. That's subtractive. Thank you. Additive is just the opposite, where you are taking the pellets or powders and you're growing your part, so there's very little waste. That's actually been around for a long time, but it was always just for making prototypes, things to test for form, fit, and function. Really not suitable for end-use parts. In the past 5 years, and most of those parts were plastics. Great for little trinkets, but not really great to put on an airplane or a car. This is rapidly changing. There's a lot of new processes, new materials, that you can make a metallic part that can be just as strong as a part manufactured in any other way. And that's where the term additive manufacturing really came from. Over the past 5 to 6 years is this migration from using printers not to make trinkets, but to make real manufactured parts. The process is really simple. High school kids get this. My senior engineers sometimes struggle with this. Is you start with a CAD model, three-dimensional model, and you create a standard file format, just like when you're using a word processor and you'll save to a PDF. In all 3D printers, you can use any type of CAD package and save it to a uniform file format called an STL. And then that STL can be then used to come up with what they call slices. So you're taking this three-dimensional model, you're slicing it into layers, and then coming up with tool paths in which you're going to start to layer by layer by layer grow your part. So one of the things that's missing in this process that's really big is there's no machine drawings. You go straight from your CAD package to the printer. To conventional manufacturing, you design the three-dimensional object, and then you have to make drawing sets that you then give a machinist to actually do the machining. That's gone. It's just simply hit the print button. So it's a radical departure from how we've made things in the past. Now, I work at Oak Ridge, and one of the questions that people ask is, well, why is Oak Ridge so interested in this technology? And in truth, I tell people Oak Ridge is the perfect place for trying to move this technology from really an infancy to its maturity. We have a lot of the fundamental scientific tools that are necessary to mature the technology. So Oak Ridge started out during the Manhattan Project. We were a manufacturing facility, taking some very scientific, fundamental research in materials and making very specific materials. 24 months, we went from the backwaters of East Tennessee. They kicked out a bunch of rednecks and hillbillies, and you had a factory of 15,000 people building materials to try to end the war. And then afterwards, a lot of the fundamental tools that we used to win the war have blossomed into some wonderful tools. We have things like neutrons. Neutrons were really important for transforming uranium to plutonium, but you can use neutrons to do things like scanning parts to measure internal stresses in those parts. And you find that ends up being very important for additive manufacturing. Whenever you're growing a part, you're melting a powder or melting a plastic point by point, layer by layer. Whenever you melt something, it expands, it cools, it contracts. So you get these internal stresses inside the parts. One of the only places to really measure that is at Oak Ridge. We can actually print a part, take it up to these facilities, the spallation neutron source, high flux isotope reactor, and I can measure the residual stress inside these parts. Also, when you start looking at 1 cubic inch of material, that's equivalent to about 5 miles of welded powder, because I'm doing it point by point. So, and the way that I melt that powder, the directions that I take, how I orient the part, how I design the part, really takes high-performance computing. The way I grow that part is going to impact its behavior. So you really need high-performance computing to be able to model and simulate these processes, which is, again, what Oak Ridge has. And then finally, it's materials. Oak Ridge is a materials lab. So we have all these fundamental building blocks that are really important for additive. And what we're doing is we're leveraging these really multi-billion-dollar public investments to help this industry mature itself. And so, again, Oak Ridge, if you're not familiar, there's about 4,400 employees, scientists, engineers. And again, we really are focusing on the materials, the neutrons, and the high-performance computing to try to mature the technology. Where I work is the manufacturing demonstration facility. And have any of you been to a national lab? I'm sure most. If you have, they're all kind of similar. Usually they're out in the middle of nowhere. They were built to try to isolate things. You're working generally with dangerous materials or dangerous processes, so they're in the middle of nowhere. They typically have a big fence around them with armed guards. This place is different. It's actually outside the lab, right in the middle of the public, and the reason is just that. We want to be accessible. One of the things that I really believe is that a lot of the national labs, not just Oak Ridge, we are jewels for our country. There are great things that are going on inside these labs, and we need to be able to have the public come in and grab it, use it, utilize it. Take the scientists and engineers that are working on things. I can't make a product, but I can sure as heck work with a company and help them make a better product. And so this facility is actually located off-site. Right now, it's a real hotbed of activity. We have on the order of $20 million worth of different types of 3D printers. Right now, I feel like a tour guide. We have about 6,000 to 7,000 visitors a year on the order of 800, 900 companies. It's a constant cycle of companies coming in because they're curious. Where is this technology going? How can I use it to make a better product? And so what we do is we show them all the different processes and help them figure out what's the right process for them. And again, leveraging a lot of the fundamentals of the lab to try to accelerate the going from a thought, a concept, to a real product. So there's three things that we really focus on. Every day when I go into work, there's three things I say, I got to at least do two of these. And the first thing is we work with the original equipment manufacturers. So all the companies that make these 3D printers, we work with them directly to try to make them more reliable. And that's one of the Achilles heels of this industry right now is in typical manufacturing, you have what's called Six Sigma, which means every time I hit go, it's going to go, right? Every time I say make a part, it's going to make a part. Right now, the success rate of these processes is like 50%, 60%. So there's a lot of scrap. There's a lot of failed processes. So we're working closely with these companies to try to look at new ways of controlling the processes, new types of feedback, to try to get to Six Sigma, to where it's very reliable. The second thing, as I've already said, is working with the companies that are interested in the technology. Company comes in and goes, I had a guy come in yesterday. He wants to make football helmets. I'm like, football helmets? He goes, yeah, he's got a design for a football helmet that will help with impact to try to keep from students getting concussions. And he thinks that additive, and I think he's right, additive can enable you to come up with designs very rapidly that could really help students and athletes in terms of concussions. So working with these companies to come up with prototypes and proving out that you can actually use the technology to develop new products. And the last thing is, as I said, we're going through a resurgence in manufacturing, right? We're starting to see an uptick in manufacturing. And there's a problem with this, is where's the workforce? A lot of students, when I was in high school, I took machine shop. We don't have machine shops in high schools anymore. A lot of these kids, I work a lot with the FIRST Robotics kids. I've had students come in and they'll use an open-end wrench and they're trying to tighten up a nut. And I'm like, here, use a ratchet. Anybody know what a ratchet is? All right, they don't know how to use it. They sit it's like, this is the coolest thing ever. Do you have another one to get it off? No, you just hook this little dial in the back and it'll go the other direction, So really trying to inspire these kids to go not just into engineering, but and not just into mathematics, but to go into manufacturing. And the 3D printers, what I'm finding over the last 5 years, the 3D printers are like catnip for these kids. Because these kids this is the instant gratification generation, right? They want it right now. Most of us that have kids, yeah, I know, right? These kids want it now. Well, 3D printers give them that. You can actually design something and print it and have it that night, all right? Now, but it also, from a business standpoint, they're also a challenging generation because they're used to cell phones. And what do you do with your cell phone every 2 years? Trade it in. So how are we going to keep these kids employed with our companies for beyond 2 years, 3 years? Because they're used to just trying something new. And these are, so there's a really exciting inflection point right now with as far as where manufacturing's going. Also, we have another thing that's going on that I've learned. We ran a veterans program last summer where we had 25 wounded warriors and veterans come in, and we trained them on these advanced manufacturing processes. They were scooped up within hours after we were done working with them. It was a 6-week program. There's over 250,000 open manufacturing jobs in the United States. Now, at the same time, I was working with the Veterans Association, there's 10,000 veterans or active duty military members entering civilian service every month. So it's like there's an input-output problem. How do we take these veterans? And for me, my best technicians are Marines. I know you're in the Air Force. I hate to say it, Marines are awesome because you just give them directions and they go. And so how do we create this new workforce? And so I think we're at a very interesting time. So with 3D printers, there's a lot of different ways that you can grow a part. You can use lasers, you can use electron beams. They all have advantages and disadvantages. There's no silver bullet. but we can 3D print metallic parts. And one of the things that we do inside our facility is we have just about every type. I'm not trying to sell machines, but what I want to do is when a company does come in to work with us, I want to give them the right advice. We can try different machines and find out what's the right one for them, because these are $500,000, $1 million investments. And the last thing you want is, much like that high school teacher getting a 3D printer and making it a big paperweight, we want it to be used. We don't want it to be a failed process. We don't want it to be a failed experiment. So let's have the government, let's have the public help the private industries figure out what's the right technology for them. So like, as I mentioned earlier, one of the things that we're really leveraging is some of the big scientific tools. So this is the spallation neutron source. When I first got to the lab, they were building this. It's a phenomenal facility. It has a linear accelerator that gets particles moving near the speed of light, and it slams into mercury, and that mercury splays off neutrons. Neutrons will penetrate anything, and you can look at how they diffract through the material to measure residual stress. So we use this process to actually look at how these different processes impact the material properties of these printed parts, because the last thing you want to have happen, how many of you fly? Everybody fly? All right, you don't want a part breaking when you're flying. And so really understanding the material properties of these additive processes is key. And so this is a video that kind of shows like a turbine blade we made for General Electric. So this is one thing we need to work on, is the audio video people get these really weird groovy music going. But this is actual data, and it's kind of like Fantastic Voyage. We can actually go in and we scan the part, and we can go back in and ride through it and look for any defects in the part. So you can see the rough surface finish, but what's interesting is when you turn the corner up here, you'll start to see what are called strata, these lines that are created by the process when you're going back and forth welding the material. We can also see these little pipes. There's some defects in the pipes. So we can do inspection that we've never been able to do before and really understand how to modify the process to get the parts that we need when we're done. Another thing that we're doing is, one of the big questions that's been asked is, can you get the same mechanical properties from these processes that you get from traditional manufacturing? And again, I don't want to make a part that's going to bring a plating down. And the surprising answer is, you can go better. You can go better. One of the things that we can do through these processes is locally control mechanical properties. So I can have a very stiff, I can change my grain structure within the material in different areas. So on that turbine blade, imagine you have an area where it has the propensity for a crack. And it looks like if it starts to crack, it's going to go to a critical area. Well, I can design the grain structure to direct that crack away from sensitive areas. So you can do things with these processes we haven't been able to do before. And as an example, one of my colleagues, Ryan Dayhoff, I'm a designer. I'm a robotics guy at heart. And I use these to really try to create, I use these processes to try to create really cool examples of where the technology can go. Ryan is a metallurgist, and so Ryan comes to me one day, and we always are going back and forth competing with each other. And he comes to me with this little block of metal, and he goes, "This is going to blow you away." And it's just a little cube, and I'm like, "I'm sorry, I need to teach you CAD, son. This is ugly." Well, what he did was, if you section it and you look at the grain structure, you can see it spells out DOE. So he can actually control the grain structure of the material, the metal, as he's growing it. This is game changer in terms of this process. We can do things now with this process we've never been able to do in the history of manufacturing. Again, my background's in robotics, so again, looking at novel ways to use it. A lot of work in hydraulics. So this is a hydraulic hand that we made for the Secretary of Energy years ago, really to start to try to get people thinking about where additive can go. The picture on the left went kind of viral. It's a robotic hand. Looks very lifelike. It actually looks kind of Terminator-ish with this mesh, but it gets into the strength of the process. Number one, with most manufacturing processes, the more material you take off, the more expensive it is. It takes energy to remove that material. You have scrap, and it takes longer. With additive, it's just the opposite. You're only using the material you need. So the lighter you make the part, the less powder you need, the less energy you need, the faster it's going to go, the cheaper it's going to go. So it really does get to this whole lighter, faster, cheaper paradigm shift. But the other thing that's really fascinating is I'm not limited to straight lines, round holes. On this hand, everybody sees what's on the outside, but for me as a designer, what's on the inside is really cool. I have a hydraulic pump, turn on the motor, the fingers will wiggle. It's a working hand, and much like the veins in my arms, the fluid is routed in very organic directions. So again, making it more efficient, making it lighter, making it simpler. We've then taken this and expanded it to a full set of robotic arms. These are arms that are all hydraulic, and if you'll notice, there's no hoses. Most hydraulic systems, when you look at an excavator or a backhoe, you got big hydraulic hoses all over the place, and those are where your leaks happen. These are hydraulic arms where it's much like, again, the human body, all the hydraulics is integrated directly into the structure. Also, we make them very lightweight. They're hollow on the inside. You take these they're titanium arms, you dump them in the water, they'll float. All right, so they're neutrally buoyant. They've been deployed out in the Navy. The Navy made these for the Navy. They deploy them on submersibles and fly underneath ships to do inspection and repair. Doing a lot with the polymer systems. Again, blah. One of the things that I wanted to get to is we've worked with a lot of the companies on the metal machines, a lot of companies on the polymer machines, and about 3 years ago we made a discovery, which is, again, as I mentioned, when you look at all of these processes, you're melting metal or you're melting plastic, and you generate a lot of residual stress, and that stress will want to make the part curl and warp on you. If any of you have ever worked with a little 3D printer, if you make a big flat part, it'll want to curl up on you like a potato chip. Well, one of the things we discovered, especially on the plastics, is if we put carbon fiber in the material, things get better. We initially did it to increase the strength and the stiffness of the part, but what we found was it changed thermal conductivity and coefficient of thermal expansion, which means I don't need an oven. All of these 3D printers are in ovens to keep the part nice and hot. I don't need it. I can do it at room temperature. The part won't warp and curl on me. And so what we started looking at is, well, how scalable is this? Can I make really big things? Most 3D printers almost all 3D printers are categorized in a couple of simple ways. First off, they're small. I can make something the size of a shoebox. They're slow. Usually you're growing parts at about 1 cubic inch an hour. So that shoebox is going to take you all day. And then the materials are expensive. They're typically $100, $200 a pound. So that shoebox is going to cost you $1,000, right? I mean, that's the where most, and whether you're talking plastic or metal, that's the fundamental problem. Also, when you look at these 3D printers, I'm a part of the Department of Energy. Energy is important. 95% of the energy going into that 3D printer is in the oven. So if I can develop new materials that allow us to work outside the oven, I'm going to increase my energy efficiency of that process by over an order of magnitude. So it's a real game changer in terms of energy. So we started about a year ago looking at scalability. So instead of making something the size of a shoebox, can I make something the size of a car? Can I make something really big? Instead of instead of having a 1 cubic foot build volume, we have a machine now that has over 1,000 cubic foot build volume. Instead of growing things at 1 cubic inch an hour, we're going over 2,500 cubic inches an hour. We're growing things, now we're measuring it in terms of pounds per hour. We're growing parts at about 70 to 100 pounds of material an hour. So putting down a lot of material. And most importantly, the cost is cheap. So I like big, fast, and cheap. The materials are $2, $3 a pound. And that's important because now if you're starting to talk about making something like the size of a car, that car may weigh 1,000 pounds. If it's $100 a pound for that material alone, it's only for the high-end market. But if I'm talking about now $2 a pound, $3 a pound, all the material going into that car is going to be $2,000, $3,000. And so that's a real game changer. So another thing that I think is important is a lot of people think that national labs move at a glacial pace. I've heard that many times. Nothing could be further from the truth. If you are motivated and you have a belief in what you're doing, we can move extremely fast. And this is one of the things that I think our society is missing, is we need moonshots. John Kennedy was absolutely awesome when he said, he was bold. He said, by the end of this century, by the end of this decade, we're going to get to the moon. And it provided focus, it provided drive. We need moonshots. And I'm a big believer in that. And so we're putting out a series of moonshots. And one of them was, can I print a car? And so this process, this whole program started just over 2 years ago. And back in January of 2014, we were making big parts, but we were doing it in a lab. And we had a company, Cincinnati Incorporated. Cincinnati Incorporated is a 116-year-old machine tool manufacturer. They make big hydraulic presses. They're not a 3D printer company. They're a machine tool manufacturer. They sold Henry Ford his first hydraulic presses. And what's great is they still work, right? 100-year-old presses still work. This is a company that is the kind of the foundation of our country. And so they came into our facility, they saw this big 3D printer, and this guy goes, I think we can make this. I think we can produce this. This is in January of 2014. So in March, we signed our Cooperative Research and Development Agreement, which basically just lays down the framework for how we're going to work together. April, they deliver their first gantry system. This is it here. It had a build volume of like 7 feet by 13 feet by 3 feet. And by May, we're printing parts, right? So literally going from having nothing to in 5 months, 4 months, we're printing big parts on their machine. Well, then we had another company come in, Local Motors, and Local Motors is an innovator in terms of cars. And this guy, Jay Rogers, comes to me, and he's watching this 3D printer, and he goes, can we print a car? I was like, I don't know why not. 30-minute conversation. He went from making very expensive cars on the order of $100,000 a piece to his target is to mass produce customized electric vehicles. He's actually building a factory up here, National Harbor. He made an announcement he's going to build a micro factory in National Harbor. And the idea is small, customized electric vehicles, where much like today, when you go and buy a car, you go into a dealership and you walk through the lot, you find one, you pick it, you go. His vision is, and that car, by the way, is exactly like the one right next to it. It might be a different color. It might have a different interior style, but you really don't have a lot of options. And that car is mass produced in a factory that's massive and then shipped, hundreds of miles to your facility or to your dealership. His vision is to go back to pre-Henry Ford. Can we have, instead of massive manufacturing facilities, his goal is in 10 years to have 100 microfactories around the United States, where it's a small town. You have factories that are not producing one type of car. It's actually, instead of one big assembly line, it's got a number of these big printers printing cars. And the vision is that you go in. Now, whether this is going to work or not, I don't know, but it's bold. But the idea is you go in and you say, I'd love to have a Corvette. I'd love to have a 1963 Corvette. And, but I'd like to change this body style a little bit. And you sit down with a designer and you design it. And then you go away, you come back the next day and it's done, right? You could say, I want to have a 1935 Buick. You could say you want to have the Wienermobile, whatever you want. It doesn't matter. It's 3D printing. There's no tooling. It costs nothing to change the design. So it's completely flexible. And then the economics are very interesting. Again, this body, the video on the top was in September of 2014. This is last year. It's crazy how fast time goes. We actually, 6 months from the time we signed our contract with Cincinnati, 5 months from the time we signed our contract with Local Motors, we're up in Chicago printing a car where they actually drove it out of the facility. And you can go online, the strategy is all over. These guys are like the pros of promotion. They're absolutely amazing. So after the Detroit Auto Show, after this show where we printed this car, I came back and the Department of Energy was wanting to have the car go to all these different places, but it wasn't ours. Oak Ridge DOE doesn't own the vehicle, Local Motors does, and so they asked a simple question: would you be willing to print a car for the Department of Energy? Dumb question, right? Of course, but we're going to do something different because a lot of questions were coming out about the car. Number one, safety. What happens when you get into a wreck? And the big question is we don't know. A lot of people think that this thing is fragile. It's just the opposite. When we were up in Chicago printing the car, I took one of the fenders and took a sledgehammer and was beating it. You couldn't break it. It's a composite. It's carbon fiber reinforced plastic. It's tough. So my concern is not that when you get in a wreck that the person is obliterated. It's just the opposite. It's not going to absorb energy. All that energy is going to be imparted to the passenger. So are there things we can do in the design to make the system safer, even safer than a typical car? And I think there are. Most crash tubes are designed to just take impact in one direction, right? They're a tube. But I could make a very organic structure. We could design organic structures that could take impact from any direction and absorb energy. And we could also do multi-material. The flexibility, the degrees of freedom you have to work with are enormous. So in terms of safety, I would say, yeah, it's not safe now. If you get into a wreck, it's going to blow. It's going to just obliterate whatever. It's like driving a 1973 Ford. You're going to obliterate whatever you hit, and you're going to absorb the passenger's going to absorb all the energy. So how do we get around that? How do we develop new systems, new cars that are printed, that are extremely safe? The other thing was the surface finish. Whenever you look at these 3D printed parts, they have like this scalloped edge. How can we get something that has a smooth surface finish? How much energy does it take to grow a car? Again, I'm coming from the Department of Energy's perspective. Energy in manufacturing is really important. And so we started this really aggressive program. This was a 6-week program, another moonshot. I had 6 weeks to go from saying, hey, you have the funding to print a car, to actually having a working vehicle, one-of-a-kind vehicle. And so the first thing we looked at was energy absorption. So we made a lot of different organic structures and found that just by changing the shape, we could significantly change the profile, the energy absorbing profile. For a crash tube, what you typically want is constant force. So as I crush it, I want to have a constant resistive force. But most tubes buckle, right? They go boom, 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 so you get this high frequency vibration. Well, we can make tapered tubes that actually give you constant resistive force. So started really looking at the fundamentals there. We started looking at the energy that it takes to manufacture something with this process. And this is a classic curve by a colleague of mine at MIT, Professor Katowski. And what it plots out is the energy intensity, the amount of energy it takes to make something per kilogram on the vertical axis, and your speed on the horizontal axis. And you get this hockey stick curve. Most high-end processes, real fine production processes, take a lot of energy and are very slow. This large-scale 3D printing is just the opposite. I can make very detailed things at a high rate with very low energy. And then the final thing was lightweighting. We were also asked about lightweighting. So the Strati weighed about 1,000 pounds. It took 44 hours to print. Can anybody guess what well, you guys know, we printed a Cobra, right? And so we were looking at lightweighting that structure, and instead of weighing 1,000 pounds, we got it down to about 450 pounds of printed parts. And this took just about 24 hours to print. And one of the funny stories behind this was we had complete freedom in terms of what we were going to make. And we could have made a Pinto, a Ford Pinto, but who would have been jazzed, excited about a Ford Pinto? My dad would have. He had 2 of them, but I don't think anybody else would be excited about it. And the interesting thing is, it would have cost me the same to make a Ford Pinto as it did a Shelby Cobra. And so as we started this process, the first week was design. And I had myself and 2 other engineers, and we didn't know what we were going to build, so we said, let's have a little contest. Let's see who can come up with the coolest design. And after day 3, we decided we all 3 would have been fired by auto manufacturers because we were terrible in terms of designing elegant cars. And so we went online, found the data for the Shelby Cobra, and started printing. The next thing was the surface finish. And so we partnered with a local company, True Design, and they started looking at coatings. So when this comes off the printer, it has kind of like, it looks like corduroy. You have this rippled surface finish. And it's cool, but a lot of people, when you think about a car, you want a real smooth surface finish. So we've been working with this company, True Design, and partnered them up with BASF, 3M, and Eastman to look at what are the right coatings. So I don't have to sand it, I spray it on, and I can get a really beautiful surface finish. And so the final product was in the upper left-hand corner, the Cobra. And one of the things that was interesting is we had to have this done we had the president and vice president in for an announcement January 9th. So that was the first target. But then we had to turn around the next day and take it up to Detroit for the Detroit Auto Show. And one of the interesting results is we had it at Detroit, where all these beautiful cars, and the first day, it's the only 3D printed car there. The first day, everybody's walking by. Nobody's asking any questions. And I'm feeling like, man, we just wasted a lot of money. My boss is going to be really mad at me, because we brought this car up here and people. And a guy comes up the second day. And I mean, literally, we had no one talking to us. And this guy comes up and goes, what's the story with the Cobra? And I said, well, it's printed. He's like, no, it isn't. I was like, yeah. And I showed him the little areas we had left. Like on the hood, you can see a oak leaf, and the oak leaf is clear coated, so you can see the lines from the printing underneath. And he said, this is crazy. And he says, you need to put a sign on this car that says, yes, this is 3D printed. So we put a sign on it. It went crazy. It went absolutely viral. And that was the fundamental test. I didn't even think about it, but afterwards it was like, this process has matured because we had people walking by not realizing it was printed. It looked so real. So now we're trying to go even bigger and even faster. So the first system we put together had a build volume of 7 feet by 13 feet by 3 feet. And we used that to print the parts for the Cobra, the parts for the Stratty. We have a new system that we're putting together. It's actually operational now. It has a build volume that's 8 feet wide, 20 feet long, 6 feet tall, and it's producing parts at about 100 pounds an hour. And our target is to print a home, a small home, one of these mini homes. We've partnered with Clayton Homes and SOM, Skidmore, Owens & Morrell. They're a large architecture firm. And what's going to be interesting is this house is actually going to be, you have plug-in hybrids. We're going to do the opposite. Instead of having the house and the grid charging the car, this is for off-grid opportunities. And it's also for developing countries. Can we have the car be an energy source for the house? Take power with you. If you look out in your parking lot, there's a lot of power just sitting there, idle. You only use your car for maybe an hour. Well, up here you may use it for 2 hours a day. But you don't use your power plant very much. And so what we're doing is we're not going to be using the Cobra. We have a new small utility vehicle we're printing that has, as the main energy source, it's natural gas, has a couple of big natural gas tanks in it, and that drives a Honda generator, which charges a battery, but also can be used for propulsion on the car. But even better is it has wireless coils that can then inductively send power to the house. So now this starts to open up some really interesting questions. I read this book by Maury Klein a few years ago called The Power Makers, and it really kind of documents the evolution of energy in the United States. And in the late 1800s, the current wars between Westinghouse and Edison, and the big solution was, look, in terms of energy and in terms of power production, scaling laws say we need big power plants. Big power plants are cheaper. One massive power plant is a lot cheaper to make than hundreds of smaller power plants. And so you go big power plant, that means you got to transmit power over a long distance. AC wins, right? But if you think about what we have today in terms of appliances, how many AC-DC converters do you have in your house? It's crazy. Your phone, we're going to LED lights. Your lights half the cost in the lighting is your power converters to go from AC to DC. So now what happens if I say, well, we can change the calculus of power production? There's a lot of small portable power units out there. We've got them in our cars. What if we use that for power? What if I can have my car, I take it with me. So I'm at home. Also, there's no AC batteries, right? Power from solar is DC. Batteries are DC. Everything is DC. We just use AC because you can transmit it over a large distance. If we change that, things get interesting. So that's this big experiment. Can we have a DC home, and can it be powered by my car so I take my power with me? Can I have localized energy storage, a battery, that does my baseline power, but when I go to work, the power demand goes up wherever people go, so you've got your power plant, take it with you. So that's kind of the nuts and the bolts. It's not just printing a house, it's really looking at a bigger problem in terms of sustainability, in terms of where we're going as a country in terms of power. What are some things that if we had a clean slate, how can we change it? So then the last thing is, again, I kind of mentioned this earlier, I love kids. I love high school kids. High school is a really cool time. You have kind of a blank canvas in terms of what they want to do. They don't know what they want to do. And so at that critical time for high school students between 9th grade and 12th grade, they don't know where their talents lie. And so just one of the things that the lab and DOE has been really great about, and I think DOT, I think you guys are starting to do it too, is outreach and invite these kids in, work with them. So this manufacturing demonstration facility I work at, we open it up every year, every winter, to 13 local schools. We have volunteers that stay from 6 o'clock until 10 o'clock every night. We open it up on Saturdays from 9 until 5 to build robots. These kids for 6 weeks will come into our facility, and engineers will work with them, myself included, side by side, teaching them how to use these tools, use these printers, and they print robots. And they then go to competitions all around the United States and compete. And so this is, again, where I get really excited, because I see in the eyes of these kids, creativity that I've never seen before. Most engineers have been trained on how to make stuff. You can't have an oval hole, Lonnie. You can't make it. Well, these kids don't know that. And this process doesn't need that. So working with these students, you can actually create a generation of engineers that is going to leapfrog all the other nations, I think. I think we have a unique opportunity. And there's something about the U.S. There's that Yankee ingenuity is kind of in our DNA. Even our kids, it's been passed along. I don't know how it's been passed along to our kids. They have a way of figuring things out. I've got high school kids getting patents on designs on their own doing. They come to me with an idea, and it's like, well, let's try it out. Let's see what happens. And it's like, damn, that's pretty good, kid. It's really exciting. So I think, creating this fire, creating this ecosystem is really, really critical. And that's the final point. It's just, I think the national labs really can be and should be an ecosystem for our country in terms of manufacturing, in terms of cybersecurity, whatever it be. But it can't be done in a silo. You have to open up to industry. You have to open up to local community, work with students, work from elementary all the way to postgraduates, work with companies, bring them in, be wide open. It's exciting. That's it.
Thank you.
No problem.
For this glimpse into a brave new world. We do have, we're recording this talk, so if you have questions, Johnny's will bring the microphone around.
Okay, great.
Wow, I have a lot of questions. That's
Bring
fascinating.
'em on.
Well, for starters, how many parts are there in a 3D printed car?
Awesome question. So the typical car, this was one that was really interesting. The typical car has about 20,000 parts. These printed cars, about 50. You have, I can literally count them out. You have your printed body, which is also the aesthetics. You can have printed seats. We have elastomers we can print out as well. So when on that Stratty and on the Cobra, you have the body and frame, because they're one and the same. 8 bolts holds the rear end on, which has your motor, your transmission, your brakes and wheels, and then the front end is your steering column. It's an electric vehicle. Steering column, wheels, brakes, and springs. That's it. It literally just 16 bolts. I can take the front end and the rear end off. One of the questions that people always ask is, what happens if you get into a wreck? I print another one. Right? The cost of the printed car is probably on the order of $4,000, $5,000. You total your car, you're going to pay more than that. I have a friend of mine, his son just wrecked his car. It's $7,000. I'm like, I just print another one, and it can be different.
Wow. A second question I had is, how many different kinds of feedstocks are there? It sounds like there's infinite possibilities for composites, but how is that going, and what kinds of materials are we talking about?
Yeah, so another great question. So typically, and most machine tool manufacturers don't sell feedstock, right? They sell machines, and then you buy your feedstock from all these other places. That has not typically been the case in the 3D printing area. The same company that you buy, 3D printer companies make money 3 ways. I call them the 3 M's. They sell the machine, they sell maintenance agreements, and they sell material. So they've choked it. I mean, I like a lot of these companies, but they've really choked out the ability to have a lot of innovative materials. That's rapidly changing. Again, and the key has been patents. Patents lapse, competition comes in, and what we're seeing now is we've worked with companies, 3D printer companies, and trying to get them into manufacturing. And what I've found with Cincinnati, and there's other companies like Ingersoll, Thermwood, Wolf Robotics, that they're machine tool manufacturers. Actually, the easier thing to do is, instead of taking these 3D printer companies and trying to get them into manufacturing, why don't we take manufacturing companies, work with them, and have a 3D printer product? Then it explodes. We've run on the large-scale polymer printer probably well over 100 different types of materials, because you can do not just all the different types of thermoplastics, but you can do composites. I can do glass fiber, carbon fiber, Kevlar reinforced, blah, blah. It goes all over the place. And you leverage the existing infrastructure. One of the things that's been really exciting is when you look at the plastics industry, it's enormous. It's enormous. And most of it goes to injection molding. And so what we're doing is we're using the same feedstock. And so now your supply chain is enormous that you can work with. Now, one of the fundamental questions that I ask is, well, so what do you do when you're done? Can you recycle this stuff? Also, it's a hydrocarbon-based material. You know, what are we going to end up with landfills filled with plastic cars and parts and whatever? And the answer is, well, there's an emergence in terms of lignin-based and bio-based thermoplastics that's really exciting, to where I can make a thermoplastic that can decompose over time. So I can print it out, and then I can throw it in a landfill, and it'll compost over 10 years, 5 years, 3 years. So really, the materials is where it's, as a researcher, I'm not a material scientist. Boy, I wish I was, because it's a rich, rich area.
Okay, so I have one more question.
Bring it on.
So what I'm thinking immediately as you say this is something that we're all familiar with, right? And that's that our little HP printer at home is the loss leader, because really it's just a way of selling cartridges of ink, right? So is that really what the business model might end up being on some of this manufacturing equipment? That's
where it is now. So like I said, if I buy plastic in pellet form, ABS on the little, that's the primary, ABS and PLA is the primary thermoplastic that people use in their home printer. You're going to pay for the cheap stuff, you're going to pay $30 a pound. I pay $1 a pound. And that's at a premium. You can get it for 50 cents a pound, because I'm leveraging an existing infrastructure. When you go to a wire, it's different. So I'll tell you right now, there's companies that are working on, can you do the same thing I'm doing on the big scale? Can you do it on your desktop? Where I can buy a bag of material that'll last me years for $50. And again, I'm leveraging that existing feedstock. That's where I think you have to go. Same thing on the metals. You know, the metals, a lot of the companies use, it's a lot like powder metallurgy. The powder metallurgy industry is, you take these powders, you provide pressure and heat, and you can rapidly create parts. All of your throw rods in your car, all your piston rods in your car are made this way. It's like injection molding with metal. Take metal powder, press it in, and those powders are 50 cents, $1 a pound. Now, most 3D printers, the problem that we have right now is there's two industries that are really driving innovation in 3D printing. And it's because of the constraints that we have today, of the slow, expensive, and small. And that's the aerospace industry and the biomedical industry. Because implants are small, and insurance is going to pay a lot for half of the hip implants in Europe are made additively. And so you can pay $200 a pound for that material. But you can't pay $200 a pound for the material that goes in an engine, in an internal combustion engine. No way. And so the question we're asking is, well, why can't I use that powder? That's the powder I want to use, because I can make big, cheap metal parts. And so we've started, again, I'm big, fast, and cheap. We've started with big, fast, and cheap plastics. We're rapidly moving towards big, fast, and cheap metal. And one of the companies we're working closely with is Caterpillar. Caterpillar looks at big excavators, and you think, why would they be worried about weight reduction? They are, because with every pound they can get off of their boom is a pound more of material that they can dig. And every pound of material they dig is profit, and it's competitive. And so all of these large companies that make large earth-moving equipment, buses and trucks, same way. It's not mass-produced. And that's one of the keys. We had a discussion earlier about, is additive, is everything going to be 3D printed? Not in my lifetime, not even close. It's really for those areas where production rates are relatively low. You're looking at hundreds to maybe thousands a year, not hundreds of thousands a day. And high-value products where, again, lightweighting is really key. And that's usually in transportation, where the lighter you make something, the better.
So you have a real culture of innovation there, and you listed a whole variety of companies that you work with, and I sort of wonder how do you manage that?
Don't. It sucks. It sucks to be.
Well, how do you make it happen then?
So you have a team. You have a team, and one thing that I've been blessed with is we have a really good team of engineers and scientists that kind of help pull the load, because literally every day I have a company in that will have a great idea, and my nightmare is dropping the ball. And so we have teams of engineers, postdocs, students, that as a company comes in, if there's a great idea, it's like, okay, you bird dog this. We had GE appliances in, and GE is looking at, I was talking earlier, there's a movement towards these smaller houses. We're getting away from McMansions to smaller houses. Well, there's one area in the house that's pretty demanding, which is the kitchen. So what's this going to mean in terms of the future appliances and future of the kitchen? So GE, actually, you can go on and Google First Build. First Build is a new program that GE has started where you as a consumer can provide ideas. And this is where additive gets really exciting. So let's say one example was somebody wanted a wine cooler in their refrigerator. All right, and so this person submitted an idea, other people submitted designs, they printed it, it works, it's now a product. But the cool thing is if you had the idea and you helped design it, guess what? You get to share in the profits. So it's becoming kind of a crowdsourcing for products for General Electric. It's really, now the one thing they had to do was they decided, we're not going to apply any patents. We're not going to patent. And you go, well, that's kind of crazy. No, you know why? We're going to move so fast. By the time somebody copies us, we're on to something else. And so one of the things is like a micro kitchen. Can I make a kitchen that has, in something the size of this podium, that has maybe a little bit wider, that has a cooktop, it has an oven, it has my refrigerator, it has everything I need for a kitchen. And can I make that efficiently and quickly? And the 3D printing is the way you can at least start with low production, start with prototypes and go to low production. And then when you get to mass production, you scale up. You scale up. But it allows you, the GE was telling us, it typically takes them 3 years and on the order of $3 million to go from a thought to a product. All right? This First Build has been active for 6 months. They've got 13 new products. All right, so it's a game changer.
Other questions?
Thank you. It's really exciting. So still on a printed car.
Yeah.
So you said that there's 50?
Yeah, there's approximately
around
50 parts, 50 to 60 parts on the electric
So
vehicle.
I guess based on what you discussed, so the number of parts we need, basically it will be determined by the feedstock, different types of feedstock.
Right.
Not by the function, because the function will be too complicated. So that's your answer to my question. Right. So that's what I'm thinking. So, from the materials part, that's I figured that's we can imagine it, but for the nerve part of the car, something as you showed the robotic arms, and those control the fingers. I didn't get how that part is implemented. in a printing process?
Yeah, so good question.
Yeah,
so right
thanks.
now, 3D printers are, for the most part, one material. So if I do a wiring harness, if I do my computer controls, those are all a part of the assembly process. But there's a big movement towards printed electronics, printed wiring, to where I can put down, as I'm laying up my structure, I can, if I understand your question correctly, I can give you an example Ford has been in. And we've talked about seats and instrument panels. And believe it or not, those are the long lead items because they're so complex. You have the wiring harness, the ventilation, your electronics, all of this in a pretty compact environment. And the question is if I can print a conductor, if I can emplace a sensor, if I can grow my ducting, it takes about 17, 18 hours to assemble a seat, about the same amount of time to assemble a instrument panel. That doesn't get calculated into the, you're making a car every 17 minutes. It's done in a different place. They bring it in and pop it in. Now, one of the big questions is, well, so I get in a wreck, and I have this instrument panel that has all of these things integrated into it. How do I recycle that? How do I get all that material out? And that's actually a problem that we have today with refrigerators. Again, I went into GE, and I've struggled with this. It's like, do I really like this idea of printing electronics directly into the structure, multi-material printing? Because I'm not going to be able to recycle that material. It's multi-material. If I melt it, it's blended. What am I going to do with this material? Mm-hmm. We have the same problem today with refrigerators. If you look at how a refrigerator, a stove, anything is made, you can't repair them. They actually will put the wiring harness inside, and then they squirt it with their insulating material, and it is frozen in there. If it breaks, you're just going to buy a new one. And so from a research side, that to me is a great problem. If we are going to move towards multi-material 3D printing, where I can have elastomers and structure, conductors, insulators, all printed in one part. So instead of having 4 different materials and then assembling it, I can do it layer by layer, bit by bit. How am I going to, when I'm done with that product, how can I get that material back? That to me is a big challenge. Mm-hmm. So I don't know if that answered your question.
Yeah, it's if I want to ask, we are printing cars. Are you thinking printing computer itself?
Not in my lifetime. But if you look at the printing, if you look at the process, it's very similar, right? Photolithography is a layer by layer process. So it's very similar. So what may happen, and that's why it's exciting to see companies like HP get into the 3D printer business, because you're starting to see some of these microelectronic companies get into the business, because the construction of the semiconductor industry is an additive process. If you look at how we make solar cells, it's an additive process. A lot of these processes, carbon fiber layup, additive process. So the question is how can you merge these to make new industries, new processes?
Hi there. In your estimate, when will we see printed cars on the public roads?
That's I think you're going to see them I'll tell you, you will see them within a year over in that National Harbor, or whatever the heck that place is over. The guy that owns it, he's a big investor. I think they're making cars for him right now. But it's going to be a neighborhood electric vehicle. Highway is a different animal because you have to, the cost of you're not going to see the big three. You're not going to see the Toyotas, the Fords printing cars. Again, not in my lifetime. What you are going to see are a lot of small companies making customized vehicles.
I'm sure we'll have some comment from our friends at NHTSA.
Yeah.
This has been very stimulating. Thank you so much.
Thank you.